So a theme from yesterday was, or last lecture was thinking about some linear algebra that you can sort of do on vector bundles. If vector bundles are parameterized vector spaces, families of vector spaces, there's parts of linear algebra, these endofunctors that work well, other parts of linear algebra, kernels and co-kernels that don't. Today we're going to do some more linear algebra. We're going to continue to focus on the vector space side of these categories that the category of vector bundles inherit from. And that piece of linear algebra is a more geometric piece, so, well, metrics. So these are essential in geometry to measure lengths and angles. And what you do, there's a few ways of thinking about it. I like to start with equipping a vector space with a symmetric, positive, definite quadratic or bilinear form. And then, because it's positive definite, it's not degenerate. So this is gives a way to an isomorphism of V with its dual. We're finite dimensional here. We can also think about that as then in any basis if we apply the function from V to R, sending some vector to the value of the form, and I like to use brackets for form, so V will be quadratic in all the coordinates. And so these are equivalent ways. We'll use this in a second. So let me go ahead and just say, suppose I have, so how do we translate between these? If I have one way is if I've got this form, then this is what I can call this quadratic function. Conversely, if I have a mu, then I can define the pairing between V and W to be 1/2. So we're in characteristic 0, mu V plus W minus, minus mu of V minus mu of W. So that's the standard very classical translation. The bilinear forms, then it's pretty clear that you can represent them by a matrix. The quadratic functions, yeah, that's also pretty obviously a matrix, and you can, a little exercise that I won't even write down is to sort of see how this works in more classical notation. So we're going to use both of these points of view, and then a metric on a vector bundle, and that's called a Euclidean structure, or makes it a Euclidean bundle in the terminology of Milner and Stasheff. Is just a is one of these is a function which we'll still just call mu from the total space to R, so that each mu restricted to a fiber, which we're calling our V's, is one of these quadratic. And what we want is for the quadratic as well, it's also going to be positive definite. I should say that. Okay. So let's go back and I want to reflect a little bit before getting into this. Let's reflect on this basic linear algebra structure. So by way of comparison, so let's just go back to linear algebra. Let's think about, so a metric is added structure, which we can think of as akin to a basis, which is also added structure. But unlike a basis, there's a couple things to say. First, so it feels fairly different. First, it's inherited by subspaces. We'll make use of that. Here's an aside. If you ever teach linear algebra, I like to, as we're doing bases, I mean, it's hard to see what the point of a basis is until you get to some application like eigenvectors, in which case it really comes home that, oh, okay, I can understand the dynamics of this linear transformation, the geometry, by thinking about it in two parts, a change of basis and then this linear transformation in a better basis. But as you're getting going, I like to just think about taking planes in R3 and asking students to find a basis, and inevitably they find different ones, and so all these things about change of basis and so forth are better motivated. So anyway, so metrics, I think of them as much simpler, easier to manage structures. One is because they are inherited by subspaces, and two is that there's a contractible space of such. In fact, it's convex. Here's where it's nice to think in terms of the quadratic, positive definite quadratic functions, because, well, first of all, between any, pick in coordinates, the convex linear combination will be given by doing by making by taking convex linear combinations of all the coefficients of your quadratic function. And so but then you're at the end, because you're doing those all together, you're just taking the values will be convex linear combinations of values. And if you're positive, if you got two positive numbers, a convex linear combination of two positive numbers is positive. So, so that's one reason it's nice, even though I like symmetric positive definite bilinear forms to sometimes think in terms of the functions. So yeah, so these are, so they're fairly different. We're going to see that unlike bases, which are very rare for vector bundles, in fact, essentially what we showed last time is that if you have a basis on every fiber, then the vector bundle is trivial, and we gave plenty of examples of non-trivial bundles. We'll see in a little bit that most bundles that we'll consider have these metric structures. Speaking about the second fact, let me just give a little exercise. This is purely linear algebra, but something I couldn't find when I was just looking up, and then feel like this needs to be classical. Give some sort of coordinate or other clear, compelling description, in particular one where contractibility and convexity is clear of the space of quadratic forms. Oops. Sorry, I needed to positive definite quadratic forms. So that's just more something I'm curious about. Sometimes I give exercises that I care to know. My students often figure them out. So let's give a couple applications of this notion of a metric on a vector bundle. One is that we can define the sphere bundle, and it, you know, S E is really, I'm choosing a metric, but we're going to drop it from the notation in general, which are all, you know, all V, so that they're of unit length in every fiber. So in every capital V, in every preimage of a point in the base, we're going to think about all things of unit length. And this is known as the sphere bundle, because in fact, it's up to homeomorphism. So the homeomorphism type is independent of the choice of mu. Again, we can now think about, you know, if you've got two of these quadratic forms, you know, they're just sort of ellipses, but you know, there's, for every line out of the origin, you know, I've got this correspondence, and that correspondence is going to give a homeomorphism. So it's again related to this convex linear relationship between them. So these are fun because these give us a better handle. I often like to think in terms of the sphere bundle because it actually affords an opportunity to use some algebraic topology or some homotopy theory to understand vector bundles. So characteristic classes are all about that, but you can be more naive and hands-on. So one thing to notice is that all of our total spaces of a vector bundle are homotopy equivalent because, well, if I've got a vector space fiber, I can take the standard homotopy between the identity map on that fiber and scalar multiplying down to 0. Again, I'm going to try to be good about saying scalar multiplication makes sense in a vector bundle, period, right? Whereas taking a basis doesn't unless you're a trivial vector bundle. Taking a metric makes sense once I'm assuming one is around, once I find one. But anyways, scalar multiplying down to 0, it makes sense in any vector bundle, and that gives a homotopy inverse to the 0 section. So there's no algebraic topology that's going to allow me to tell the difference between B and E, but sometimes then SE, which is a homeomorphism invariant of the isomorphism type of E, sitting over B, those can be interesting. So those can be non-homeomorphic and in particular non-homotopy equivalent. So here's a good example. So sometimes these SE can be sensitive to vector bundle non-isomorphism. An example of this is if I take the Mobius bundle plus the trivial bundle of rank 1, I'm going to start calling those epsilon consistent with Milnor and Stasheff. And I think about the sphere bundle. Now, since you're watching this in a video, let me give us, this is an example. I'll say it in a second, but hit pause. What is that sphere bundle? All right, hit pause. Now you're back after hitting pause and you're ready. You either figured it out or you didn't, but I claim that this is the Klein bottle. Yeah, I'll just, I think I won't give any further explanation. So it's a little exercise as we go along. And so that's not the same as the sphere bundle for the rank 2 bundle over the circle. So therefore, and this came up in my class at the University of Oregon yesterday, mu plus epsilon is not the same as epsilon 1 is not the same as epsilon 2. So another application that we can make is sorry, let me, oops. Sorry about this. Another application we can make is to, when we now have a subbundle, which again, we don't always have the image of a morphism of vector bundles is in a subbundle, but sometimes you have a subbundle around. So another application is, so if we have a subbundle, then we can define the orthogonal complement as the subspace, the other subbundle of F of things which are perpendicular. So W in F, so that W inner product with V is 0 for all V in E. So so that's really important. A key example there is if M is embedded in N, then the tangent bundle of M is a subbundle of, take the tangent bundle of N and restrict it to M. And in which case, then we define the normal bundle to M to be the quotient of, or we're going to take the tangent bundle of M perp inside of the tangent bundle of N restricted to M. Okay. But as I said, quotient, let me give a little exercise here. First, just verify E perp is a bundle. Maybe you're tired of verifying things are bundles, but if you're not yet, as is, I don't think we covered this yet, as is F mod E, and then show that they are isomorphic. Great. Okay. So metrics are actually easy. And the reason is, well, let me introduce a bit of notation. This is not in Milner and Stasheff or anywhere. Maybe, you know, maybe if somebody wants to look up and inform me if there is a standard name for this. I'm going to call it a Tame vector bundle. I was choosing between terms such as good, small, sub-Euclidean, compact, embeddable, but I settled on Tame vector bundle is one which is isomorphic to a subbundle of a trivial bundle. In other words, we can embed it in a trivial bundle. For some n. So pretty much everything we're going to do in this class is on tame vector bundles. Let me give you a exercise, proposition exercise. All vector bundles over compact, or more generally paracompact bases are tame. I'll come out and be honest, I can't really, I don't know of a good example. Well, I can give that as an exercise too. It's fun. We can just example of non-tame. So yeah, so really I'm going to teach you about tame things because I haven't really pondered non-tame things. But then by what I said about, well, obviously quadratic functions can be restricted or bilinear forms can be restricted, then it's clear that all, you know, corollary, all tame vector bundles. This is, I guess, just a, yeah, corollary of nothing. So I'll just call it still a proposition, but it's very easy. All tame vector bundles have a metric, some metric. And then any two metrics, again, will sort of differ by, you know, we can think of a path in this convex space, and so they'll be isomorphic. So yeah. So essentially, there's homotopically that always exists, and so it's not empty. It's unique. So homotopically a point. So somehow there's a metric is almost, if you're a fully homotopy, if you're thinking fully homotopically, metrics are sort of canonical objects. So then the other thing that we can say is that, I guess a corollary of this is that we can choose transition functions. Because once you've put the metric on, then if you look at the transition functions under that, with that choice of metric, then, well, what we're calling our transition functions, remember, for every U and V in an open cover over the intersection, we have, for every point in the intersection, we have a matrix. So, so we have this map from the overlaps to GLN, and what you can do is say that, oh, okay, well, if we have a consistent notion, think again just of the unit spheres, then it's those identifications we can actually make through the orthogonal group as well. And another way to see that these are sort of homotopically, there's no choice, is that this is a homotopy equivalence. The homotopy inverse, one homotopy inverse given by the Graham-Schmidt process, which is, yes, an algorithm, but it's continuous in the input variables. And so the orthogonal group includes in GL and R, but that's a homotopy equivalence. So, so yeah, again, I want to contrast the imposition of a metric with putting a basis or even naming a single coordinate on a vector bundle. Naming a single coordinate giving a non-zero section, that's dicey, because coordinates under transition functions, they change, whereas the inner product structure can be made to not change. That means that that's essentially equivalent. So it goes the other way around. Suppose you can reduce from GLNR to ON. In fact, you can use Graham-Schmidt. That would be an alternative route of proving that every the tame vector bundles have some metric. Although again, I think that you need the tameness. It's equivalent. You might think that Graham-Schmidt would give it in general, but I don't think it does. Um, uh, so in any case, those transition functions then do preserve the metric. And again, they also preserve being zero. They also preserve lines. So we're going to play some other games where to a vector bundle, again, I can't talk about all things with the first coordinate equal to whatever, but I can talk about the collections of lines inside a fiber and things like that. So, so yeah, that's going to be part of our perspective in general. What is preserved under these matrices? Well, metrics in general aren't, but homotopically they are. So that's the main point here. Let me give 2 more exercises. That's about all I wanted to do for new material this time. 2 more exercises. One is one of my favorites in basic topology. Well, first one, just to kind of warm up, you get, here's a fact that E over B has a non-zero section if and only if the sphere bundle, again, for any choice of metric, has a section, just a section. And again, you can imagine, right, this could give an alternate proof, for example, that say the Mobius bundle is non-trivial, or doesn't have any sections, sorry, because you can use then, in order to have a section, I'll let you think through various examples actually. In order to have a section, that would mean that for the sphere bundle, then the projection back down will be the identity. So that means that the homology of B is a subobject of the homology of the sphere bundle through the map, which through this projection. So for the Mobius bundle, that projection is multiplication by 2, and then there's no homomorphism from the integers to itself. That is the inverse to the multiplication of by 2. I'll let you think about other examples, but this again is a sort of more hands-on way rather than the whole theory of characteristic classes that we'll get to discuss some of these things. Another exercise, again, this is one of my favorite. Show that the following are homeomorphic, that the unit tangent bundle of S2 is homeomorphic to, yeah, I don't know which, well, let me write them more symmetrically, RP3, or the group of 3x3 orthogonal matrices. These are all the same space, which is one of my favorite little facts. Okay, I think that's what I would like to end with, and I'll see some of you on Monday.